So hello to my fellow engineering students. So my name is Cristel Lyka Abalos from BSCE 4C. So today I will be discussing the FLEXURAL members, which is sample problem number 1. So let's proceed. So allow me to read the problem first. So determine the allowable flexural strength AST and the design flexural strength LRFT of a W18 by 35 A992 steel having a continuous lateral bracing. So for the solution, we have some following steps to follow. So for the step 1, we have to list first the relevant properties of W18 by 35 A992 steel based on the AISC table. So kapag na-list na natin yan from FY to CW, so makikita natin siya sa AISC table. So after listing the properties of W18 by 35 steel, we may now proceed to step number 2. So that is check for compactness of the given steel. So to determine whether the steel is compact, non-compact, or slender, gagamitin natin yung width thickness ratio na tinatawag. And this is based naman on the NSCP 2015. So for solution of unstiffened element, which is the flange. So determine the width thickness ratio for flange. I-divide lang natin yung base sa thickness ng ating flange. So lambda is equal to B over T, or which is BF over 2TF, or yung twice ng ating thickness ng flange, is equal to 152 over 10.8, and we will have the lambda of 7.037. So base lang, yung base natin is all over lang sa twice of the thickness. So yun ang ating lambda. So for our lambda P, 0.38 square root of E over Fy. So saan ba natin itong nakuha yung formula na to? So this is according to the NSCP 2015 table 502.4.1. So dito natin makikita yung mga value for limiting with thickness ratio. So kung saan ba siya nagpo-fall, yung description of elements. So we will have 0.38, square root natin yung E natin, which is 200,000 all over the 345, which is the Fy. So we will have a lambda P is equal to 9.149. So for lambda R, 1.0 square root of E all over 345, we will have 24.077. So as you can see, yung lambda P, yung lambda natin is less than the lambda P, which is 7.037 is less than 9.149. So kapag mas malaki kasi yung lambda P natin sa lambda natin, therefore matatawag natin yung flange natin is compact. So next, for the stiffened elements, which is the web, yun ang ating stiffened elements. So the width thickness ratio of web, lambda is equal to H over T. So dito naman natin makikita yung height or yung depth sa ating web element. So H over TW is equal to D, or yung depth natin, minus 2K all over the TW, or yung thickness ng ating web. So saan ba natin nakuha itong formula na to, which is H over TW? So kung babalikan natin kasi yung table 502.4.1 sa ating NSCP 2015, ating code. So for case number 9, maka-classify natin yung ating steel section. So the H is the distance between two flanges, or the height. So since naman given properties of steel yung H. So for this case, kinuha lang natin yung overall depth ng ating web. Then minus natin yung 2K or the thickness of the two flanges. So based on the formula, substitute lang natin yung given value from the properties. So, 450 minus 2 times 21 all over 7.62. We have 53.54. So, yun ang ating lambda. So, for lambda P, 3.756 square root of 200 over 345. We have 90.53. And for lambda R, we have 137.24. So, as you can see ulit, kapag mas malaki yung lambda P natin sa lambda, matatawag natin na web is compact. So, after natin maklasify na compact yung both the flange and the web, so we may now proceed to step number 3. So, step number 3, solve for the nominal flexural moment. So for the plastic moment, MP is equal to Fy Zx. So saan ba natin nakuha yung formula na to? So also, this is based in the section 506.2.1, which is yielding. So where MP is the plastic moment, Fy is specified minimum yield stress of steel being used. And then Zx is the plastic section modulus about x-axis. So lahat ng ito is based on the AISC table. So sa properties ng ating steel. So to determine the MP or the plastic moment, so by substituting the given value to the given formula, so MP is equal to Fy times Zx. We have 3,760,500. So now, nakuha na natin yung plastic moment ng ating steel. So the next step is to compute the lateral torsion buckling. So meron tayong mga limitations na nakaset sa ating code, which is the NSCP 2015, which is to compare the LB, LP, and LR, where LB is the unbraced length is equal to 0. So based on 506.2.2 lateral torsional buckling, since ang value ng ating LB is equal to 0, automatic ang makukuha nating value ng LP is greater than 0. So therefore, LB is less than LP is less than LR, and then where MP is equal to MN. And since hindi naman nag-a-apply yung lateral torsional buckling natin, and wala tayong dapat i-consider na lateral torsional buckling, automatically the plastic moment will be equal to the nominal flexural moment. So where MP is equal to MN, so magiging same lang sila ng value, which is 376.05 kilonewton meter. So for the last step, after natin ma-determine yung ating nominal flexural moment, so the last step is to compute the design strength Mu and allowable flexural strength Ma. So we have the value of Mn is equal to 376.05 kilonewton meter. So that is computed before in step number 3. So yung unang hinahanap sa problem natin is the design strength Mu using the LRFD. So where reduction factor is equal to 0.90. So we will be having reduction factor times Mn is equal to 0.90 times natin yung Mn na nakuha natin kanina. So we have Mu is equal to 338.5 kilonewton meter. So last na hinahanap sa problem natin is the allowable flexural strength MA using ASD. So where the reduction factor for ASD is 1.67. So MA is equal to, divide lang natin yung MN natin na nakuha natin kanina sa 1.67. So therefore, we have MA is equal to 125.18 kilonewton meter. So that's it for the sample problem number 1. So for the sample problem number 2 for flexural member, so let me read the problem first. A simply supported beam is subjected to a uniform service dead load of 15 kilonewton per meter, including the weight of the beam, and a uniform service live load of 30 kilonewton per meter. So the beam is 12 meters long and is lateral supported at the midspan, and a 572 grade 50 steel is used. So the question is W30 by 108 adequate? So assume TB is equal to 1. So based on the figure, nakikita natin, the length of the simply supported beam is 12 meter long. So to determine if the W30 by 108 still is adequate, so first step is to list the relevant properties of the given steel. So same lang sa ating problem number 1 kanina. Lilist muna natin yung mga needed properties for this problem. So these properties of steel is based on the AISC table. So after listing, so pagkatapos natin ma-list lahat ng properties na kailangan para ma-solve natin itong problem na to, we may proceed to step number 2 for the second step, which is the checking the compactness of the steel section. So let's check if the elements are compact. So for the unstiffened elements, which is the flange, so refer tayo to the table 502.4.1 in the NSCP 2015. And we will be using B over T for the width thickness ratio of the flange. So we have lambda is equal to B over T or BF over 2TF, which is 267 over 2 times 19.3. We will be having the lambda of 6.91. So for the limiting width thickness ratio, let's assume first that the element is compact. So bakit ba natin ina-assume na yung flange natin is compact? So mostly kasi kapag galing sa NSCP 2015, the elements are compact. So ina-assume na doon na lahat ng elements doon is compact. Siyempre pag nag-design tayo. So therefore, we will be having the formula of lambda P is equal to 0.38 square root of E over Fy. So by substituting, we will be having the lambda P of 9.16. So since ang ating steel is grade 50 steel, ang ginamit nating Fy is 344. Since lambda is equal to 6.91 is less than lambda P is equal to 9.16, therefore the flange is compact. So for the stiffened elements, which is the web, so for width thickness ratio of web, so lambda is equal to D over 2K all over TW. So by substituting the given value to the given formula, we'll be having the lambda is equal to 49.67. So for the limiting width thickness ratio, let's assume first that the element is compact. Yun yan kanina. So therefore, we will be having formula of lambda P is equal to 0.38 square root of E over Fy. So lambda P is equal to 90.66. Since lambda is less than lambda P, therefore the webs are compact. So after natin ma-determine na yung mga elements are compact, the third step is to solve for the nominal flexural moment. So for the plastic moment, MP is equal to Fy multiplied to Zx. So based yan sa ating section 506.2.1 yielding. So where MP is the plastic moment, Fy is the yield stress of steel being used, and Zx is plastic section modulus about x-axis. So we will be having plastic moment is equal to 1,950.48 kilonewton meter. So for the unbraced length or LB, based on the problem kanina, the beam is 12 meters long and laterally supported at the midspan. So sabi, midspan daw siya. So ang LB natin is equal to 6 meters. So limiting LP and LR, where LP is equal to 1.76 square root of E over Fy, LP is equal to 2.317 meter. So for the LR, we will be having this formula for LR. So by substituting all the values coming from the properties ng ating steel, we will be having LR is equal to 6722.79 millimeter and approximately 6.7 meter. So for LP is equal to 2.317 meter, is less than LB, which is 6 meter, and less than LR, 6.7 meter. So therefore, it is under case 2, which is the formula for computing the nominal flexural moment is this. So by substituting, we will be having the value of Mn is equal to 1,302.50 kilonewton meter and is less than DMT, which is yung nakuha natin kanina na 1,950.48 kilonewton per meter. So for the last step for this problem, we will be computing the capacity using LRFD and ASD. So for LRFD, where reduction factor is 0.90. So reduction factor B, Mn is equal to 0.90 times natin yung Mn, which is 1,302.5. Meron tayong capacity sa LRFD na 1,172.25 kilonewton meter. So for ASD naman, ang reduction factor na gagamitin natin is 1.67. So meron tayong capacity using ASD na 782.93 kilonewton meter. So since the beam is simply supported, meron siyang distributed load. So for dead load, ito yung formula natin. MD is equal to weight ng dead load times yung length natin squared all over 8. So by substituting, the weight of the dead load is equal to 15 kilonewton per meter and the length of the beam is 12. Squared lang natin all over 8. We have MD is equal to 270 kilonewton meter. So for computing live load, ML is equal to yung weight lang ng ating live load times natin yung length squared over 8. So by substituting, the value of weight of live load is 30 kilonewton per meter and the length is 12 meter squared lang natin all over 8. So we will get the value of ml is equal to 540 kilonewton meter. So based on the code for LRFP, design strength must be less than or equal sa ating capacity. So for ASD naman, yung allowable flexural strength natin must be less than or equal sa capacity, which is applied moment. So let's compute yung ating design strength. So for the design strength, MU using LRFP, we will be using the given load combination based sa ating code. So MU is equal to 1.2 times the dead load plus 1.6 times the live load na nakuha natin kanina. So by substituting, meron tayong MU is equal to 1,188 kilonewton meter, where yung ating MU is greater than the capacity. So therefore, the section is not adequate. So sabi kanina, the design strength must be less than or equal sa ating capacity. Kapag less than siya, the steel section is adequate. Pero dahil yung ating design strength is greater than the capacity, the section is not adequate. So allowable flexural strength MA using ASD, we will be using the load combination ML. So for allowable flexural strength MA using ASD, we will be using the load combination MA is equal to dead load plus live load. So MA is equal to 810 kilonewton meter. So where ang ating MA is greater than the capacity, therefore the section is not adequate. So for this problem, ginamit natin yung dalawang design, which is the LRFP and ASD. So both of them ay nag-fail sa ating section. So it is not adequate. So that's all of the discussion for the sample problem for flexural members. So thank you.